For a linear system, the critical point type determines the phase portrait entirely. For nonlinear, it only determines it locally. So we'll take an example, look at an example and see how this works. So for this particular system right here, it's defined by some polynomial equations. And so when we go to look for the critical points, let's see, so the first equation, y minus x times 1 minus x minus y being set equal to 0, that's going to imply that either x is equal to y or that y is equal to 1 minus x. And so combining this with the other equation, that one implies that x equals 0 or y equals minus 2. Oh, and now I'm getting into my picture, so let me move that out of the way there. So from that, we can see that the critical points are going to be 0, 0, 0, 1, and minus 2, minus 2, and 3, minus 2. So those are the different possibilities, just looking at all different combinations that are allowable. And so let's go ahead and plot these. So there's the origin, that was 1. And then I had minus 2, minus 2. And 3, minus 2. And 0, 1. And so now by looking at the original equations and just plotting points, I can find out. So for example, let's take x to be 0. So we're looking on the y-axis right here. Then that's going to zero out the y prime. So we'll just have a horizontal vector. And by checking the signs, I can see that the horizontal component is going to be positive if we're in here and negative elsewhere. So this is the way things are flowing. And if we look along the horizontal axis where y is equal to 0, then we find out that over here things are going up, and over here things are going down. And by evaluating at a few more points, I find out that it's kind of, so we're going pretty steep over here. And then as we come across, it gets sort of flatter and flatter. And let's see, so coming down here, it's, let's see, so like this. So this is all just stuff that I found by basically plotting points. Okay, blah blah blah, bunch of stuff. So now putting this together, what we end up with, let's see if I can draw some of this here. So we actually have a curve coming across the bottom, and we also have something that goes, okay, let me see if I can figure out how to draw this here, up and over and around and down. And we have something going down this way and something going down this way. And so these guys are going up and these guys are going down. This is going all the way around. Um, and then we have some kind of very interesting thing going. Let's see if I can draw this here. Like that. And like that. Woo! Okay, all kinds of good stuff. So now I'm gonna color a couple of these slightly differently here. So these ones inside, I'm gonna actually make them. Let's see, maybe does red stand out? I will go with pink. And so the reason for that is because so these ones here. This is called a separatrix. And the reason why is because it separates trajectories which are qualitatively different, meaning that they converge to different critical points. So, in other words, everything that's in the orange region here, this is what's called the basin of attraction for this particular critical point. If it starts in the orange, it's going to tend to this one that looks like a spiral point up at the top. If it starts outside on the other side of the pink separatrix, it's going to tend to this point over here. So if I look at, so this is, let me see, let me just label that. So this region here is called the basin of attraction. For 0, 1. And so if I start anywhere inside there, like say at this point, the solution curve is going to come up and it's going to tend in as time goes to infinity. Other curves look like this. Well, those are a little wobbly, but there we go. So there's a bunch of potential curves, and so now let's see what's going on. So if we look sort of up close and shoot. There we go. Okay, so if we look up close and personal at this guy, it actually looks like a spiral point. Yeah. And if we look up close and personal at these other guys, we see that this guy here is some kind of a node. Wow. And so, in fact, this guy is a what we would call a sink. Everything tending into that particular point right there. And over, let's see, on the other side here, this is going to be a source. So here we've got something that looks like so this one's a source, this one's a sink, this one's a spiral, and I've figured out what the last one is here. This guy's actually a saddle. So he's got the one coming this way and the other one coming this way. And there we go. All right. Oh, and I guess that's our separatrix right here. So this is coming in and the other one's going out. Okay, so that's a pretty good comprehensive picture for this guy. I think I took way too much time drawing that, but oh well. It's a pretty picture. Well, okay, so it's a pretty ugly picture, but it's got lots of interesting stuff going on. So let me just write down that definition that I mentioned before. So the basin of attraction or region of, so this is also the region of asymptotic stability So the basin of attraction for a critical point x naught is, or actually, you know what, let me change the notation here. We'll call it a critical point P is the set of all initial points x naught where if you start at that particular point, then it implies that the limit as time goes to infinity of phi of t is equal to p. So then a trajectory on the boundary of a basin is called a separatrix, because it separates the trajectories which tend to P from those that don't. Okay, and so now boundaries of attraction can actually be quite complicated. And so I'm going to show you a picture of what happens for a pendulum with 3 magnets. So this is called the chaos pendulum, or a nonlinear pendulum. So here's the idea. Suppose we're looking from above and we put like a red magnet here, and we put a yellow magnet here, and we put a blue magnet over here. And then we have a pendulum, and the pendulum can be started from anywhere. So if I start the pendulum right here, it'll just spiral into the yellow one, right? And if I start it over here, it'll just spiral into the blue one. But if I start it somewhere in between, it might do some sort of curious thing and end up who knows where. And the trajectories you can get are quite weird. And so if we start it from here and it ends up over at the red one, then I'm going to color this initial point red. And if we start it over here and it does some loopy thing and ends up on the blue one, then I'm going to color that initial point blue. All right, so now let's take a look at what this thing gives us. Okay, there it is. So this is a pretty crazy picture here. In fact, it's fractal in nature in the following sense. Between like where the blue region here and the yellow one meet, there's a thin sliver of red in between them. And between that thin sliver of red and the blue, there's a little sliver of yellow, and so on and so forth. So the more you zoom in, the more detail you find. And there's never a region like you can't find one color touching another, because the third is always somehow in between them. It's pretty nuts. And so this stuff over here where you see there's like all these little fine lines intertwining each other, that indicates that there's an infinite sensitivity to initial conditions. Because if you start your pendulum in some place, well, you really can't tell if it's over the yellow or the blue. The slightest little perturbation, or the red, will result in the pendulum ending up stopped over a different one of these magnets.